Okay, so let's do the next part. So we're going to consider a different type of optimal stopping problem, one where the one-step look-ahead rule isn't necessarily going to work for us. So here, we're going to look at a type of stopping problem where we've got x of t as a symmetric random walk on 0 to n, okay? So you can think of this as some sort of random stop price or whatever, and we've got to decide when to stop, okay? Now, here, it's a random walk on 0 to n, so it goes up with probability half and down with probability half, and if it hits the end points, 0 or n, the process is automatically stopped, okay? Now, we can assume for each state in this set there is a positive reward, Rx, for stopping. Okay, so we're looking at a maximization problem, maximization of rewards rather than minimization of costs. Okay, so slight twist there. Okay, and we're asked to maximize, okay, the expected reward from stopping at time capital T. Okay, all right. And what I'm going to first ask to do, we're going to characterize the solution of this, but what we're first asked to do is to show that the optimal value function is something called a concave majorant. Okay, so what's that? Okay, so we've got a definition of that up here. Okay, so definition of a concave majorant. Okay, for a function R such that goes from the set 0 to n to the real numbers, or in our case, positive real numbers, a concave majorant is a function g such that g of x is bigger than r of x. So in that sense, it's a majorant. It's bigger than r of x. Okay, and it's also concave, meaning that the value of the function g of x is bigger than half the value of the point below it, and plus a half the value of the point just above it. Okay, so let's just draw a picture of that quickly. So what I'm saying here is if we've got our states x over here, and I look at g of x on this axis, and I've got x, x minus 1, and x plus 1, okay? And let's suppose the value of g of x is this, at x minus 1, and the value of g of x plus 1 is here, okay? I can look at the average of these two numbers, okay, which is essentially just drawing a line between these 2 points and taking the point in between. That gives this. Okay, we need the g of x to be bigger than this point. Okay. In other words, what's going to happen is if I plot all the points that g takes, it needs to look like a concave function. Okay, so just to recall what a concave function looks like, that means if I have x and g of x, concave function looks like this. It looks like a cave, okay? It doesn't have to go all the way back down. It could keep on going off this way, but basically it keeps curving around like this, okay? Convex functions are the functions that go the other way, okay? And the way to remember what a concave function is, it looks like a cave, okay? So you can also have a little caveman inside with his little fire, okay? So that's how you always remember what concave means. Okay, right. Anyway, so back to our question. So the first thing we want to show is that the optimal value function, the maximal value of this, is a concave majorant. Okay. All right. So we're basically going to go through the steps of characterizing the optimal solution for this problem. Okay. So for this, we're not going to be going with one-step look-ahead rule. So one thing we can do, which I also ask you to do, is to write down the Bellman equation for the problem. Okay, so the Bellman equation for this problem would be that we want to find the optimal reward, R of x, okay, and it's equal to the maximization over the actions we can take. So we maximize over the two things we can do, which is either stop or continue, okay? Now, if we're at state x and we stop, then we get a reward as given by the problem of R of x. Okay, so that's the reward we get for stopping. Okay, and the other action is to continue. Okay, now for this problem, there's no continuation cost. There's just a stop or continuation reward in this case. Okay, So we just have to look at the expected value of the reward from the next state. Okay? So we're looking here for the expected value of the reward if we allow to continue one more step. Okay? So two things can happen there if we decide to continue. Either half the time we go down a step, okay, and then we look at the optimal reward from that point onwards, or half the time we go up one jump to r of x plus 1, to x plus 1, and the reward from there is r of x plus 1. Okay? That's the Bellman equation for this. Okay? We said that we have to stop at the endpoints at 0 and n. Okay? So there's no action to take there. So r of 0 is equal to r of 0, and r of n is equal to little r of n. Okay? Since we said that we can't take any further action once we've hit 0 or n. Okay? Right. So we can see just from the form of this solution that we've got a concave majorant. Okay? So why is that? Well, we've got two conditions here. That the function value has to be bigger than half up and above of that function. So we've got the function r of x is bigger than a half up and down of that function. Okay? So tick concave, okay, and it has to be bigger than r of x. Okay? So tick majorant. Okay, so from this, we see that the function that we're considering has to be a concave majorant. Okay, so that's that part of the question done. Okay, so now we want to characterize exactly which concave majorant we're dealing with for this optimal value function. Can we characterize it a little bit more than just saying it belongs to this class of functions? Okay, so in fact what we're going to show is it's the minimum such concave majorant. Okay, so how are we going to go about doing that? Okay, so what we're going to do is we're going to start from the process over s steps, okay, and show that for any concave majorant, that function must be less than that concave majorant. Okay, so that's what we're next asked to do. So show that, and I've crossed that out, apologies, typos. Show that r of s is which is the optimal reward function starting from x, and stopping before s steps, okay, where if we actually take s steps and we stop, then the reward we get is 0, okay, then that optimal reward function for stopping over s steps is less than g of x for any concave majorant g, okay, so let's show that, okay. So, okay, answer for that part. Well, firstly, we're going to show the result essentially by induction. Okay? So, first, we've assumed that r of 0 of x is equal to 0, which is certainly less than g of x for all concave majorants. Okay? Because we said that g of x has to be bigger than little r of x, and we said that little r of x, okay, is positive always. So something 0 has to be less than something that's positive. Okay? Now, continuing our induction, suppose that r of s minus 1 of x is less than g of x for all concave majorants g of x. Okay? Then let's show it's true for the next step. And again, the idea is to apply Bellman's equation. Okay? So it's a finite time problem. R of s of x is the optimal value function when you have to stop over s steps. Okay? So we can compare this with the optimal value function over s minus 1 steps, in a bit the way we did the exercise on Bellman Ford, or the way we looked at Markov decision processes in finite time. Okay, so either we stop, we've got two actions, let's write down the Bellman equation for this. So either we stop now, in which case we get a reward of R of x, okay, or we continue one step, half the time we go down one step, and half the time we go up for one step, okay. But notice we've expended one of our steps, okay, so we've got f steps to stop, and if we continue one step, then we've got one less step to go through. Okay, so that's the Bellman equation now for this type of problem. All right, and we've assumed now that R of s minus 1 is less than g of x. Okay, so we've assumed that each of these guys is less than g of x. So it's less than the max of R of x and a half g of x minus 1 plus a half g of x plus 1. Okay, but the thing we know from the assumptions we've made about g being a concave majorant is that g of x is bigger than this. Okay, so it's bigger than this term here, and g is bigger than R of x. So g of x is bigger than this term. Okay, so we know since both g of x is bigger than both of these two items, that this is less than or equal to g of x. Okay, which is what we wanted to prove. So it's true at time 0, and if it's true at the previous time, it's true at the next time. So it must be true at time 1, 2, 3, all the way up to s, and for all other s's. Okay? So in other words, the optimal reward function for stopping over s steps is less than any concave majorant. Okay? So we've got that part done now. All right? So now, want to use that fact to show that, well, if it's less than any concave majorant, then maybe the optimal value function is in fact the minimal concave majorant, the smallest one that we can choose. Okay, so let's show that. Okay, so here we have the question asks, show that the optimal value function, v of x, I've called it v of x here, I was calling it r before, so slight shift in notation, my apologies, show that this is the minimal concave majorant, and it is optimal to stop whenever that minimal concave majorant equals R of x. Okay, so let's do that. In fact, it's not too hard from this point. So we know that value iteration, and notice this is exactly the steps here, are exactly the steps of value iteration. We know that value iteration converges to the optimal solution for positive programming. Okay, so the value iteration converges to the optimal function. i.e. R of s of x goes all the way up to v of x as s goes to infinity. So by the last exercise, so by exercise 59, v of x is less than g of x for all concave majorants. Okay, so we know that R of s is less than g of x for all g of x. We know this goes up to v of x. Okay, so this must imply that the optimal value function is less than g of x. Okay. And we also know from 58 that v of x is a concave majorant. So we've got something that is a concave majorant but is less than or equal to all concave majorants. So v of x is the minimal minimal concave majorant. It's the smallest one. Okay. Further, from the Bellman equation, we know that if v of x equals little r of x, then it is optimal to stop at x. In other words, if we look at our Bellman equation here, I should have written these with v's rather than with capital R's. Anyway, if v of x is equal to little r of x in here, it's saying, well, of the actions, stop or continue, it's better to stop. Okay? So whenever this is true, it is optimal to stop. Okay? So now let's just draw a picture of actually what we've found. So what we have so we've got the values of x from 0 to n, and then we can plot over here the values of little r. Okay, so let's first plot little r of x. So it's just some set of points. Okay. Okay. And then we found that the optimal value function is the minimal concave majorant. So that's the smallest concave function. So let's assume that's 0 here. The smallest concave function that fits above all these points. So what does that look like? Well, something like this. You basically just imagine putting kind of like an elastic band over the set of points and seeing where those points lie. Okay, so in particular, if we kind of sat an elastic band over all of this and pushed it down, it would essentially lie, sorry, excuse my drawing skills, that's meant to be a straight line, it would lie essentially on, and again bad drawing skills, over all these points. Okay, so it'd go boom, 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 it'd be a bit more like this, the line itself, it's bad at drawing. Okay, and it would miss out the points that are kind of in between but below any specific values. Okay, so then it would say, essentially pull this elastic band over the sets of points, and then every point that that elastic band stops on, it's optimal to stop when you visit that point. Okay, so if you start here, then you'll either hit here or here first. Whichever you hit first, you stop. Okay, and that gives you optimal stopping policy. Again, notice this isn't a one-step look-ahead rule because there might be many points between these two. Okay, so you can't just necessarily look one step ahead for this type of problem. But again, it's got a very nice structure where you can make decisions about when to stop or continue. Okay, right. Okay, so that's everything that I kind of wanted to cover about the main sort of theoretical points about optimal stopping problems. And then next time we're going to start to work towards doing the continuous time versions of these sorts of problems. Okay.